Hello and welcome to this video. So a quick recap of what we've done in the previous two videos. First, we created a T flip-flop called a toggle flip-flop. We used a D flip-flop to create that by connecting the NOT of the outputs, that's the inverted outputs, connecting the inverted outputs to the D input, such that we are left with a single input called clock and a single output called Q, or whatever it is we choose to call it. So that's our toggle flip-flop. Then we created a test bench and used ModelSim to run the simulation of the test bench. So we tested our T flip-flop inside the test bench to see that it performs the way we expect it to perform. We also included a clear asynchronous input and a set asynchronous inputs that are not dependent on the clock. Two comments I'll raise before I go into the next step. Next, we want to talk about the ripple counter. But before I do that, I'll raise two comments. The first, if you look at this, after doing your compilation, this is our T flip-flop entity. After compiling it, if you expand the analysis and synthesis block, expand that, go down, you see netlist viewers. Expand that. Under that, you see RTL viewer. If you double click on that, that pulls up a schematic of Quartus's interpretation of your VHDL code. If you look at our VHDL code, in our VHDL code, we simply specified a T flip-flop with an entity called myTFF, and we said if there is if your clear signal goes low, then make my output 0. If your set signal goes low instead, make your output 1. Otherwise, if there's a rising edge of the clock, then toggle whatever was on the output. Now, looking at our RTL viewer, in our RTL viewer, what we see is that in interpreting that code, Quartus decided that it will make use of a D flip-flop. That's what you have over here. It could make use of a D flip-flop that has a clock input, has a synchronous clear that we did not use, has an asynchronous clear and an asynchronous preset. So we see that the asynchronous clear is cleared by its active low. It's cleared by a low signal, but the preset is active high. It is set or preset by a high signal. Our clock is connected to CLK of the D flip-flop. Note that this is not our T flip-flop. This entire thing here is our T flip-flop. Okay, is Quartus's interpretation of our T flip-flop. The output of this D flip-flop is sent to our output Q, which is proper. There is no Q bar from this D flip-flop, so this Q that came out is inverted and sent into D. This bubble specifies inversion, so it's inverted and sent into the D input, which is what we expect. So far we're good. Let's look at what else shows up over here. If we send a low clear signal, asynchronous signal, it comes and goes straight to the asynchronous clear of the D flip-flop. So that also is fine. But what is all this? What's this AND gate doing here? Now remember, this preset signal is active high. If we send a low set signal here, it inverts it before it sends it into this AND gate. Now, whenever this clear signal is low, this output will definitely be low. But whenever this clear signal is high, the output is dependent on your set signal. So if your set signal is low, if your set N signal is low, then when you invert it, it is high. It means you have two high inputs, your output will be high. So this is active. So set N being low means active high. That is correct. If your set N signal is high, it is inverted, it comes in low, your output here is low, this input is not active. So this system simply implements our VHDL code over here. This VHDL code is implemented as that RTL subcircuit that we've seen over here. So just take note that whatever VHDL code you have, you can take a look at the RTL viewer. In some cases, that may help to explain what is going on. So, okay, so that's the first thing. The second thing was I mentioned that these are asynchronous inputs, your clear and your set are asynchronous input. They are asynchronous because they happen outside the rising edge of the clock. Now we could just tweak this just a little bit. So let me bring this signal, this piece of code here. I will put it inside after the rising edge of the clock. So I'm going to bring it in here and say if, so else if rising edge of the clock, then check where your clear signal is active. If it is active, then we want to clear our SQ. Else, so if it is not active, then we now toggle. Okay, then we need to end this inner, this nested if statement, and I think this is fine. So what I want to do is I want to recompile this because the code has changed. I now have to recompile it, and then we'll take a look at the RTL viewer and see how our system has changed. So it's this is a good practice to see how Quartus now interprets our system. RTL viewer. Now this is what it looks like. Take note, it has brought in a multiplexer instead now. So here, it's interesting that even the synchronous player is not used at this point in time. Notice that your now we have an active low preset. Okay, active low preset, your set simply gets connected to your active low preset. That is still asynchronous, and that is perfectly fine. When your clock signal comes in, your clock signal goes into your D flip-flop. Your output of your D flip-flop gets sent to a multiplexer. Now, the output of this multiplexer is either 0 or 1. And the output, so is either 0 or the NOT of Q. Your Q signal is coming into the second input of your multiplexer. Okay, the NOT of your Q input is coming to the second input of your multiplexer. So if your clear is 0, then a high. Okay, this is 1H0. Okay, so this here is simply saying a it has 1 bit, so H0, and then it's a high signal that is sorry, just give me one moment. Is this a high signal? Is this a low signal? This actually talks about one. It's 1 bit hexadecimal, and this is 0. Okay, so we're sending a low to your D input. If the clear signal is low, then we send a low. That's we send this input here, which is 1H0, which is actually a low. It is 1 bit hexadecimal 0. Okay, it's 1 bit hexadecimal 0. We send that into your D input so that the clock coming in will send that input, which is 0, to the output. Notice now this is a synchronous clear, so that it will not clear until the clock signal comes in. When your clear input goes low, it simply tells it, okay, put a low at this D input. And this D input does not get transferred until your clock signal comes in. So when your clock signal comes in, that low will get transferred to the output. And no matter what the output was before, the output will now be 0 when your active clock transition comes in. If your clear is high, on the other hand, CLRN, if it is high on the other hand, then the NOT of your Q, which is what is connected to this input, is what gets connected to your D input. So this is what your circuit now looks like if we decide to make your clear signal a synchronous signal and your set N signal asynchronous the way it was before. Okay, so just take note that you could have your clear and preset could be synchronous or they could be asynchronous, and the way they'll be interpreted or the way they'll be implemented is dependent on the way you write your code. So what I'll just do is I'll come back here and undo everything I did here, because I like my set and preset being asynchronous in nature. I'll just compile this once again to just make sure I've not introduced any error, and then if this runs through cleanly, then we'll move on to creating our ripple counter. Okay, so that's fine. We'll create our ripple counter now. So remember, we have our T flip-flop. Our T flip-flop has one input, which is a clock, and it has, we could say, one output, which is our Q. Okay, so one input is a clock, and one output, which is a Q. Now what we want to do is we want to create a ripple counter. I'll just simply make it a 3-bit ripple counter. So I will make use of 3 flip-flops, 3 T flip-flops. That's the first. I have a second here, and I have a third down here. Okay, remember this is the planning phase. The planning phase of any project is the most important phase of that project. So I'm going to make use of a number of signals. This will be my entire counter here. This will be my entire counter here. So my entire counter, let me call it ripple C. Ripple C, ripple counter. So ripple C. That will be the name of this project, the name of this entity. Okay, it will have one input that will be CLK. I won't bother with clear and set. It will have 3 outputs. The 3 outputs will be Q. Well, I'll call them Q. Okay, 3 outputs, and I'll call all of them Q. But there'll be a Q, not a Q1 and a Q2 if you want. But the 3 of them, I'll simply call them Q. One will be connected to the LSB, will be connected to the Q of the first. The next significant bit will be connected to the Q of the second, and the MSB will be connected to the Q of the third. So I'm going to create signals. I'll call this S underscore Q0 and S underscore Q1, and finally S underscore Q2. Then I'm going to create another signal to connect this clock to this. I actually don't need a signal for this, but I'll go ahead and use a signal for it. S underscore CLK. Okay, next, to make this a ripple counter, what we want is the inverted output of one T flip-flop to clock. Let me just call this Q0, Q1, and Q2. We want the inverted output of a flip-flop to clock the next flip-flop. The inverted output to clock the next flip-flop. So I need an inverter. This signal here, remember, is still your SQ0. The output of this, I'm going to connect to the clock here. Let me call that SCLK1. Okay, so I'll make this SCLK0, and this will be SCLK1, the signal between the NOT gate and the clock, and the second clock, the clock of the second T flip-flop. I'm going to replicate that over here. So we'll have a NOT gate connected to the clock, and I'll call this S underscore CLK2. Is there anything I've left out? I think this is about all that we need. We know that we have a ripple counter. Okay, so we have our, this is not all. We still have some things we need to specify. Our T flip-flop entity that we have already declared, that we've already created, has asynchronous presets and set inputs. Okay, so we had signals that are called CLRN. Each one of them has CLRN. Now, because the entity has CLRN, we have to specify what we are connecting it to here. Now, for my actual ripple C entity, I don't intend to clear at any point in time, so I can simply connect this to a 1. I'll simply connect a 1 to my CLRN, and I'm going to do the same to my SETN. I'm going to connect a 1 to each one of these. So I do apologize, it's going to be a little messy. Okay, so I'm going to connect a 1 to each of my set n inputs. I won't write all of them here. So each of my set n inputs, I'll also connect a 1. So we could create a signal. This I can't just simply say I'm connecting a 1 to them. I have to make that a signal. So maybe I'll make that signal S underscore async. I'll make it exactly the same signal, so I won't have two separate signals. This is S underscore async will be connected to this line down here. Okay, so I do apologize. This is a rather messy diagram, but if you followed me as I was drawing it, hopefully this makes a lot of sense. So let's go ahead and create this. First of all, we need an entity that has one input and one output. So let's create, I'm going to close this project and create a new project. So creating a new project inside counters. Okay, inside counters, I will make a subfolder folder called ripple C. Name of this particular counter will be ripple C, and I'll say next. It does not exist. Do I want to create it? Yes, please. Empty project. Go ahead, make it an empty project. I want to bring in a file into this project, and I want to bring in TFF. We created a folder called TFF. Ignore this ripple C. I wrote that code some time ago, but TFF is what we created a little earlier in the previous video. So let's bring it into this project. Okay, so we'll bring it into this project. Next, 10M50DAF484C7G. Next, simulator, I will use a test bench in here, so I'll specify ModelSim Altera as my simulator, VHDL. Next, and we will finish. Okay, so now under files, we have our TFF here because that's what we brought in here. If we look at the hierarchy, ripple C is still our top level entity, but inside our files, we have our TFF. So we could open the file here if we want to modify it. That's perfectly fine. We could open the file here. So, but let me create Control N, a new file, new VHDL file, and now create my entity here, library IEEE, use IEEE.standardlogic1164.all. Entity ripple C is entity ripple C. Ports, there are two ports. The first port is called CLK. It is an input port. Its type will be standard logic because it has just one bit. The output port we call Q, and the type will be standard logic vector. It has 3 bits, so that'll be 2 down to 0. Okay, so I'll save this as ripple C. Architecture. What's the architecture like? Now, in this architecture, we're going to need to bring in this component called TFF. So let's open, that's why I opened this file here. I'll copy this here. Because I'm going to simulate in ModelSim, I'll need to bring it in as an entity. Let's specify the name. Entity, say rip of ripple C is begin and architecture rip. Okay, so now I need to bring in my components. Just specify components. Okay, then I'm going to need a number of signals. We need SCLK0, SCLK1, SCLK2. We need SQ0, SQ1, SQ2. We need async. Each one of those are single bits, but my async will need to be initialized as high. So we have SCLK0, SCLK1, SCLK2, SQ0, SQ1, SQ2. Type is standard logic, and I'm initializing them to 0. Then I have a signal called S_async. Type is standard logic, and I'm initializing this to 1 because those signals, those ports were active low, so I initialized them to 1. Next, I need to do a port mapping here. Now, we're going to need to do 3 port mappings, one for this component, another for this component, another for that component. Each time we have a new map, it specifies we're bringing a new component. So I'll call this TFF1, TFF2, or TFF0, TFF1, TFF2. Those labels, those are labels and not very consequential, okay? So my TFF port map, and inside the TFF we have CLK. We're mapping CLK for the first TFF. CLK is mapped to SCLK0. The Q of that first TFF is mapped to Q0. We also have to map the asynchronous inputs. Set N is mapped to S underscore async, and CLRN is mapped to S underscore async. Okay, I think that's about correct. So I'll just copy that and paste that twice to reduce the amount of typing I'll have to do. The others are called TF1 and 2. The clock of the second is connected to SCLK1, okay, and the output is connected to SQ1. The async is fine for the others. Okay, so far so good. We have done our internal connections here, but I still need to connect my SCLK0 to this CLK here, and I need to connect my SQ0, SQ1, SQ2 to the output of ripple C. So my SCLK0 is connected to CLK of ripple C. Now, it might be a good idea to call this something different so that we know which it is, but this is a concurrent statement, and so since it's not inside a port mapping, it refers to the entity that owns this particular architecture. So CLK of this entity, remember it's an input, it's mapped to SCLK0. Then we need to map our output. Q of the entity is mapped to S underscore Q0, S underscore Q2, that's the MSB first, S underscore Q1, S underscore Q0. In case you're wondering, the ampersand sign means concatenate. So it concatenates well, it does a concatenation of SQ2, SQ1, and SQ0, makes them into a vector, and we'll write that to Q. Okay, and that's it. We're done. We've created our ripple counter. We're done completely. We've created our ripple counter. Next, we want to do is to create a test bench for this. So I'm going to create a test bench for this. Again, it's a new entity, so I need to specify the library that we're using. Use IEEE.std logic 1164.all. Entity test bench. I'll just leave it as test bench. Is entity test bench. Architecture test ripple C of test bench is begin and architecture test ripple C. Okay, we're going to need a number of signals in here. Typically, the number of signals we need here is dependent on the number of signals, number of ports rather, that the entity we are testing has. I'll bring in the entity we are testing, ripple C, bring it in as a component. It has 2 ports, so I'm going to specify 2 signals here. Signal S underscore CLK. Type is standard logic, and I'll initialize it to 0. Create a second entity S on a second signal S underscore Q. Type is standard logic vector 2 down to 0, and I'll initialize it to 0 as well. This is one way to initialize a vector to 0, and no matter the number of bits the vector has, it will assign each one of them to 0 if you write it this way. So next, we can just simply toggle our clock. So wait for 2 nanoseconds, and then SCLK is equal to SCLK. Oh no, sorry, there's one more thing we have not done. It's equal to not SCLK. Oh, okay, 2 things I have not done. It just occurred to me. First of all, this has to happen inside a process. Okay, so there are 3 things now we haven't done. Process begin, and then end process. Then we need to do a port mapping of the, so I'll just call it M1 of the component RPL C. We need to map it to show how we are connecting its port to our signals. So we're connecting CLK to SCLK, and we're connecting Q to SQ. Okay, so that's the second thing we've not done. And the third thing, and very important, there's something major that I left out. This architecture is incomplete. Reason is this: I have specified how the clock of the second flip-flop is connected to SCLK1, but I have not specified what SCLK1 is, apart from the fact that I initialized it to 0 here. Remember, we said SCLK1 is the knot of SQ0. SQ0 is knotted, is inverted, and that's what becomes SCLK1. So we need to specify that, and that's a concurrent assignment. So SCLK1 is knot of SQ0. SCLK2 is knot of SQ1. And I think now we are done. So I should probably use a for loop for this instead of copying and pasting. Okay, so this should be fine, and let's just and run analysis and synthesis to be sure that there is no syntax error in this. If there's no syntax error, then we'll go ahead and open our simulator, ModelSim. Okay, so that's good to know. No syntax error in this. It's almost strange to write a piece of VHDL code with no syntax error in it. Okay, ModelSim has opened up, and I will recompile it in ModelSim because I want to ensure that my RPL-C entity, the architecture of the RPL-C entity is available to me. Okay, so 0 errors, 0 warnings, that's good. Work test bench is what I'm interested in. Okay, so test bench, RPL-C, yeah, has the architecture RIP, but test bench is actually what I was interested in. I wanted to make sure that this architecture shows up in here. So I want to simulate test RPL-C. Simulate. There are two signals here I'm interested in, so I'll simply right click on that add wave and SQ add wave. Okay, so let's simulate this for say 40 nanoseconds. I think that should more than cover. Actually 20 nanoseconds will probably suffice, really. We'll go simulate this a couple of times back to back. So let's go ahead and run this. Yep, so it says run the simulation. I'll zoom full. Let me run a second time. Zoom full. Now take note that it just keeps on, it just runs your test bench over and over and over. So we can see it is running through the various states as we expect. 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, all the way to 1, 1, 1, and then cycles back to 0, 0, 0, which is exactly what we expect. If we click on this plus button, we can expand it and see Q2, Q1, and Q0. And we see this is exactly what we expect. This is the ripple effect that we keep getting. When your bit 0 is crossing from 1 to 0, that sends the second, that toggles the second signal, because we are inverting the output of the first flip-flop, we're inverting and sending into the clock of the second flip-flop. And remember, we're using rising edge in each case. So the falling edge of the Q of the first flip-flop becomes a rising edge of the clock of the second flip-flop, and that causes it to flip. Now, since we as well have this code, we could ask the question, what if we had not, what if in our definition here, we did not include this knot? So let's say we took our Q directly. The Q of one flip-flop is sent directly into the clock of the next flip-flop. What will happen? Well, we have a simulator. Let's go ahead and simulate it. Oh, sorry. So resetting that, and next I need to compile this code once again. So compile, 0 errors, 0 warnings. Let's see. Do I need to refresh this, or can I just run this? Let's run, let's see. No, I think I need to refresh this. So simulate, end simulation. Are you sure? Yes. Let's come here to compile once again. Ripple C. No, okay, so hold on. Before I compile, let's update, update, and compile. Compile Ripple C. Compile 0, 1, and 0 errors. Okay, that's good. Simulate Ripple C. Test Ripple C. We want clock and we want SQ. Go ahead and we're going to run this for, well, we ended up simulating for 40 nanoseconds. Let's do it for 40 nanoseconds. We run this and zoom full. Okay, now see what happens. Now it doesn't run, it doesn't count upwards. Instead, now it is counting downwards. So if you wanted to make a down counter, all you need to do is take the output of one flip-flop, one T flip-flop, and connect it to the clock of the next flip-flop. Do not invert it. If you invert it, it counts up. If you don't invert it, it counts down, apparently. So that's the beauty of a simulator. You could go ahead and just see what it looks like. Now I'll come back to, remember we compiled it in ModelSim, not in Quartus. So I'm compiling it here once again because I want to look at the RTL viewer. So you could take a look at how Quartus understood our code, interpreted our code, and how it would try to implement it on the FPGA. Netlist viewers, RTL viewer, and now you see this. We have three entities. Our clock comes into my TFF0. Remember, we labeled it TFF0, TFF1, and TFF2. That's the labeling that we had in our port mapping over here, TFF0, TFF1, TFF2. Now, that is one reason why it is important. So it becomes a lot easier to identify each of the components that we have inside our top level entity. So our input clock comes in here. The output Q down to 0 takes its output from the various subentities. Okay, you see that nothing, or rather we connected a high to each one of our set and our clear, 1H1. Okay, so it's 1 bit, hexadecimal 1. So we're connecting a high to each of the sets and clears, so none of them ever gets set, preset, or cleared. Let's click on this plus to see this what's inside. Now this is what you saw earlier on, and we recognize this already as our myTFF entity. Okay, so you could see what is happening inside any of the sub-entities inside the diagram. So I think that will be it for this video, and this is your ripple counter. We've seen it ripple, we've created a ripple up counter, we've created a ripple down counter, we've created a test bench to test this. In the next video, we'll go on and create a synchronous counter. Ripple counters are also called asynchronous counters. We'll create a synchronous counter in the next video. Thank you.